Swayam Prabha. Digital India. Educated India.
So that's a nature wind wave part we have done. Now we are coming to look at the wave transformation. The readings, which is relevant to this content, we have all those readings here as well. And also we are able to, after you learn this one, understand the transformation of the waves and also under the changing water depths, or if there is any obstacles or some like current. So basically it's the current interactions. So Professor Raj also mentioned all this like a transformation before, the deformation. So the effect include the refraction, shoaling, reflecting, and also the diffraction. So we are also going to go through some of that. So shoaling, refraction, diffraction, reflection, and the wave current interactions. But I think we don't have enough time to cover all of that. We will focus on the first three. So first we look at the refraction and the shoaling. So for the shoaling, actually, it's a change in wave height due to the water depth change. So normally when we're looking at the water depth is getting shallower. And the refraction is a transformation of a wave height and direction due to the varying water depths. So we will see the refraction as well. So I'm not looking at this example. So when we are looking at the shoaling, we can use energy propagation to do a little bit analysis on that. So we have the energy flux at these two locations. So that's a location 1. So that's the first location and the second location. And of course, you have the energy flux at the 2 different locations over there. Then we look at the energy change, or gradient of the energy. So that's a gradient of the energy, right? The EF over dx. So that's for this 2 location change. How does the energy change? That will be the dE over there. But when the bottom friction is very, very small, so very smooth bottom, and also there's no wave breaking, then we will have a very minimum dE. So basically dE will be close to 0. Then we will be having the next equation over here. So when you're having this equation, you are able to have, basically, is energy in these 2 locations is equal. So they don't have the energy loss. So we assume they are the same. And also from yesterday, we know the energy flux will be the total energy E1 times the group velocity, and will be balanced by in the second location E2 times the group velocity 2. So that's how shoaling we are able to get the calculation. And also we know the energy, right, is a 1/8 rho g h squared. So that's 2 locations. So this is for the first location, this is for the second location. If the wave height is no change, then the group velocity has to be the same. Correct. But of course, you know, when the water depth is different, the group velocity is different. So we have a shoaling coefficient over here. Then you got the K, we use the Ks to represent the ratio between these 2 locations, the H2 over the H1, which is same as the square root of the 2 group velocity at these 2 different locations. So that's how the shoaling equations you derived. basically is from the energy balance, then you get this. So the assumption is no friction energy loss, no breaking waves. So the energy is the same at these two locations. So you maybe will ask, the Ks is, what's the value of a Ks? Shoaling coefficient, yeah. So it's always less than 1 or greater than 1. So the wave height will be bigger or smaller. So we plot out, we're using the calculation, we plot out that. You can see when the water depth is very deep, and of course, you can ignore those level change. So very close to 1, right? Because group velocity will be the same. But the transition area, so some you can see that is less than 1, and some is greater than 1. So the range actually varies. So which means some location the wave height is higher and some is lower with the energy change. So that's what we are able to do the calculations. Basically, that's because of the group velocity variation we are having. And then we look at the refraction. Refraction is a change in the wave direction and the height due to a wave encounter varying water depths along its crest. So that's the diagram you are able to see. If you have a wave propagated, then through this, based on the bottom topography, you are able to see how the wave direction will be changed. So because this is a deeper offshore and near the shore will be shallower, so you are able to see the wave direction change. So this is a typical diagram you are able to see. And using this simpler diagram, you are also able to see. If considering the figure of this one, this is a shoreline, and normally we know the bottom contour is generally is parallel to the shoreline. But if you have a certain wave coming, the wave direction, for example, over here is coming to, there's an angle between the wave and the bottom contour lines, then the wave direction will be changed. So if you look at the 2 point A and B, the wave celerity is slower in shallow water, and therefore the moving slower than the B point. So B will be moving faster compared to the A point. So the wave direction will be changed. Eventually, it will be more parallel, the crest will be more parallel to the bottom contour. So that direction will be changing. So that will be the refraction. And also, we use a way to define. We know the wave crest, and then there is a wave ray. So that's a wave ray. So this line is a wave ray, which is a orthogonal form to the wave crest. So that's you are able to define it. And then if you're looking at the contour line at the bottom, over here, the dashed line are the bottom contour line. And then how the wave ray propagated. So it can be like a converged or diverged, depends on the bottom contour lines. Yeah. So typical things you are looking into over here. The first one you are having over here is a divergency. So it will be changing and then diverged. So you are able to see the divergency in this area. But you can also see if the bottom contour lines, the shape is like that, then it will be converged. It will be converged. And when they're converged, like this one over here, the energy in the converged point location, it will be have the higher waves, right? But if it's a diverged, then the waves will be lower or decreased. So that's a refraction. And then if we look at this one, do you expect the wave at location A to be larger or smaller than those at B? So A will be smaller because the waves will be diverged. And in the B, the waves will be converged. Then you will have a higher waves. And again, we are also able to use a wave transformation to do the analysis of the energy again, but this time we are using for the refraction and the shortening. So we are able to get the refraction coefficient. That will be depends on the angle, okay? So one is a theta, and then is a theta 2. So for these two angles, it will be different. And then you will get a refraction of those two. So then you are able to calculate the wave height at the shallow water, which will have one is a Schilling coefficient, and another one is a refraction coefficient. So we are able to get to the calculation of that. Now we look at the example for the refraction and Schilling. A wave is 1 meter high. A period is 15 seconds and is in deep water. Propagate shoreward at an angle of 30 degrees over plane sloping bathymetry. Assuming that linear wave theory applies, what will the angle of the wave crest be relative to the coastline in the water depth of 3.5 meters? Original, that's in the deep water. Then when it comes to the shallow water, what the angle will be. And the second part, what is the wave height in this 3.5 location? This is a typical wave transformation from deep water to shallow water. Here involves both the Schilling and the refraction. So we will do the calculation on that. Okay, so we quickly draw the diagram. I can draw this diagram. So this is a location. This is a water depth. It's a H2, 3.5 meters. That's a shallow water. And here is a deep water. And over here, the H1 equals 1 meter. And also the period is 15 seconds. And what else we are having? Yeah, so basically, this is a location 1, and this is a location 2. We want to calculate H2. And also, we have theta 1 as well. We want to calculate theta 2 as well. So this is a cross-section diagram, but when you are looking at the plane view, so what is look like a plane view? So we will have the, so I use a dashed line. That's a slope, right? So we will have initially the wave crest over here. So we will have theta 1. So this is a wave crest. So we will have this theta 1, and then we have this is a wave crest, and this is bottom contour. So in the shallow water, here is the shallow water. So here will be theta 2. Okay, so that's what we can look at as a plane view. And over here, H2 is a 3.5 meter, and here is a dip. So we don't need to write the figure. So we are using the Scholling equations and the refraction Scholling equation. We will have H2 will be equal to H1 times Ks and times Kr. So we have the relationship. So we have the sine theta 2 over sine theta 1, which equals C2 over C1. And also we have the Kr, which equals to cosine theta 1 over cosine theta 2. And what else we are having? We also have Ks equals to square root of Cg1 over Cg2. And what is a Cg? Cg will be equals to half C plus 2kh over sinh 2kh. And when in deep water, so in deep water, remember the equation in deep water, Cg1 will be equal to half C0, which will be half L0 over T. That's very deep water, right? So we will be able to have that calculation. So L0 will be equals to GT squared over 2 pi. So I just skip the steps. Then we have this is a 351.3 meter. Then we will be able to calculate Cg1 equals to 11.71 meter per second. So similar techniques we are able to do that for. Okay, similar techniques we are able to calculate the same thing for H2 equal to 3.5 meter. We are able to calculate Cg2, which will be equals to what? So again, we will have K2 equal to 2 pi over L2. And then we have L2 equal to 87.59 meter, and then we will have K2 equal to 0.0717. That's a wave number you are having. So based on that, we are able to calculate C2. I skip all those calculations inside. So you are able to do that from yesterday's wave linear theory. So we will have our GC2 will be equal to 5.72 meter per second. That's the speed. So based on this one, we have Ks equals to 11.71, 5.72. So that will be 4308. So that's the first Ks we have. Then we have the Kr. So the Kr will be equals to cosine theta 1 over cosine theta 2. But what is a theta 1 and a theta 2? We are able to use the previous equation you are having. Theta 2 using the sine theta 2 over sine theta 1, which equals C2 and C1. Now we have C2 and C1. So we are able to have our theta 2 because we know theta 1. So theta 2 will be arc sine, and here will be sine theta 1 over C2 over C1. So we will have that is 7.2 degree. So Kr will be equals to 0.9343. So H2 will be equals to H1 times Kr times Ks. So one of that is greater than 1, and another one is smaller than 1. So you are able to see these 1 meter deep waves after it's transported or propagated to the shallow water, the wave height is 1.34 meters. But when you're taking into the refraction effect and the Schelling effect, one is actually the refraction effect. The factor is 0.93, is a smaller, but the Schelling effect, the waves is a higher, is a 1.43. So that's how you do the calculation of this. But this everything is under ideal situation, is a linear wave theory, no energy loss. Then we get this relationship. Now this is an example. So for the diffraction, is where the wave energy spread out along a wave crest from a region of relatively high energy to a region of relatively low energy. And also the region of the lower energy typically exists due to there is an obstruction in the path of the waves. For example, like island or breakwater, like this diagram, you are able to see. So if you have the wave propagated, and then, so here will be the diffraction effect. And same thing over here. You are also able to see over here. So how are we able to quantify this diffraction? Yeah, this is a breakwater. That's another typical things you are able to see. So one is a wave is over here. You have, you also have this area over here. So that's another typical diagram you are able to see. So the diffraction effect. But how can we do the calculation to find out because of those diffraction effect, what the wave height will be. So the diffraction coefficient we are defining, of course, will be the wave height inside this area and to the outside. This is the HI, and then, of course, you have HD in this location. So what's the ratio between that? That will be the diffraction coefficient. And also, of course, you know, it will depend on a different dimension and also different wave property as well. So what are they? So first thing will be the theta. What is the theta over here? Theta is the angle of the approach at the breakwater head. So that will be if the wave's coming from here, and this will be the angle, the theta. And also it depends on what? The beta over here. Beta will be the location. So if you want to know the location over here, and then that will be the angle of the beta. So if you want to see location of here, what the wave height will be, and then of course that will be the beta angle. So that will be the beta. Then also depends on the wave property, that's wavelength, and also the distance from the head of the breakwater. That will be, if the location is here, then that will be the distance from this point to this point. Or if you want to see over here, then that will be the distance from here to here. So that's the parameters you are having, theta, beta, and also the ratio between the distance r and the wavelength. So that will be the parameters you are going to look at. But it's so complicated. How can we do the calculation? In engineering application, we have this different diagram for us to use. So this is some simplified structure. So if you have a breakwater over here, this black line over here, and you have the wave, this is the blue lines are the wave crest, and then propagated in. That's a theta equal 90 degrees. This diagram will be only used for the 90 degree. And for all of this location alone, this red line, that's k equal to 1. Okay? And then you have all those different lines, that's 0.9, 0.8, 0.7, and so on. That's, you can see, 0.08. 0.08. So you are able to read all those different. At different location, you are able to get the different value for the k. So if, for example, if I want to know over here, the location, then of course you have to know what is r over here, and then what is the angle over here. Then over here, the k will be 0.1. So if the wave over here is 2 meters, and then over here, that's only 0.2 meters. Does that make sense? So that's how you look at this whole thing. Of course, further away, the wave will be smaller. And in this area, the wave will be larger. And outside, most of that is a 1. Occasionally in this region, you have a little bit even greater than original, 1.05 and 1.10. That's how you read the diagram. So this is in this circumstance. Then if you look at, if the wave is coming from here, it's a 60 degree. So this theta is a 60 degree. If the wave is coming from here, then this is another diagram. You are able to see. Again, this is a red line. That's for the k equal to 1. And then you are able to see all those different parameters over there. And most of this part over here, that's like a 1. But you are able to look at this diagram this way. So in engineering diagram, they have already drawn all those different incident wave angle. They have a 30-degree theta diagram, so you then use that. So you're able to use all of this for the analysis. So now we look at the example. Consider a train of waves with a period of 6 seconds. So this wave period is 6 seconds, and height is 2.2 meters. Approach a breakwater head at the angle of 60 degrees. The water depth in the lead of the breakwater is 10 meters. And ask you to determine the wave height at an angle of 30 degrees from breakwater, and a distance is 96.6 meters from the breakwater head. So which diagram we are using? So we are able to use this one because the incident wave angle is 60 degrees. So we are going to use this one. So when we are looking at this one, okay, so again, so we will see we use a simple diagram to show. So that's our breakwater over here. And we have the wave coming. So theta is a 60 degree. And also we know here the incident wave is 2.2 meters. And also we have what? Okay, we want to know at this location over here and this location beta, which is a 30 degree. And the distance is a 96.6 meter. We want to know HD over here. So this is a simple diagram we are able to see. And also we know the water depth is 10 meters. So by using this one, of course we will calculate diffraction factors or coefficient. So KH, which is HD over HI. So we are using the diagram. And then we need to calculate what is R over L, right? But before we're doing that, we need to calculate the L. What is L will be equal to? So we know the wave has a period of 6 seconds. And also the H is a 10 meter. So we are able to use what? The dispersion equation to calculate the wavelength. That's from yesterday. With a linear wave theory, we are able to calculate that wavelength using the dispersion equation. So I skip the detail of that calculation. But then we will be able to find out what is R over L, which is 96.6 over 4, which is a 2. So that distance is 2. Now we go back the diagram. So we know that is a 30 degree, that's on this line. And that is a 2. So it's over here. Over here, that coefficient is between these two lines. It's between 0.3 and 0.25, correct? It's over here, so it's between this line and this line. Correct. So I would say, I would take those values is a 0.28. So from the diagram, using that, from the diagram, and K will be equal 0.28. So maybe you read is a 0.27, so that can be a little bit different. But we know definitely between 0.3 and 0.25. So that's from the reading. So based on this one, we are able to calculate the wave height in this location will be so you are able to see, because of that breakwater, the wave height is much smaller inside. It's only 0.6 meters. At the breakwater head is a 2.2 meters. So that's due to the diffraction effect. The wave height has been reduced. So this is a diffraction examples. Okay, so if no question, we just keep going on. That's another similar equations. Now we look at reflection. Reflection. That's obvious when the waves is like encountered or meet an object. The wave energy will be reflected back, right? So then it will be interact with the keep coming incoming waves, and then we may have some like new setup of the waves, because you have waves that keep coming and then reflect back, then it can form like standing waves. Yeah. But because depends on this object at the end, a lot of times, some energy will be absorbed or has been lost due to the material of this one. If you think about, if at the end is like a sponge, the porous structure, then some energy will be absorbed by this one. You won't get the fully reflected energy. Okay, so that's how you analyze this circumstance. So if you have two components, so one is like incoming waves, another one is reflected waves, and they superpose together, that's you are able to get a standing wave like this. So this is a simple diagram for you to look at. One is a node, one is an antinode. So when you are looking at a node, that's a zero surface displacement. Velocity, vertical velocity at that location is a 0. So then you are able to see where that's occurred. So normally it's like a quarter of the wavelength from the wall, and then you are able to see that first point over here. That is where is that happened. Then of course, next one, that will be the half. The total will be, this will be the half of the wavelengths. So if you're looking at this, this is for the 100% reflection. As we mentioned in realistic one, normally we won't be able to get a fully reflection. So if you only have partial of the energy has been reflected, then you will get the wave shape like this. You will have over here, it still have a certain range of the amplitude. It won't be like at the node point, everything's at 0. And also you still have this like an anti-node. So that will be the partial reflection. But how can we use these partial reflections to get some wave parameters in the experiment? So for this one, you will be able to see this coefficient, the reflection coefficient, will be the ratio between the reflected wave and the incident wave. So of course, that will be smaller than 1 if you have this type of the circumstance. Then we look at the example over here. So in a wave tank with regular waves, a wave probe is moved very slowly and perpendicular away from the shore, which is 0 meter. The output of the slow-moving probe is showing the figure below. From the figure below, we are trying to get the wavelength, the incident wave height, and also the reflect coefficient. So this is the experiment data you get. Now I'm asking you to, from this diagram, to find the wavelength, the incident wave height, and also the reflection coefficient. How are you going to do this one? So over here, this is the end. So that will be the reflection wall. And then here, this will be the node. And then if you're looking at here, that's anti-node, yes. That's from our observation of the result. We are able to get this. So in last slide we mentioned where the node will be happening. 0 velocity. So where is this one? L over 4, a quarter of the wavelength. Yes. So also you see, this is a distance along a flume. And also you know here is a wall. So from this diagram, you are able to see up to here, this is a 1 meter. So you will know the wavelength is 4 meters, right? So this is one way for you to estimate the wavelength. So that's easy for you to look at. So if we going to having here, so I just maybe write over here. So the wavelength, so here is 1 meter from the diagram. So from the diagram, from the wall to the first node, so we will have L equal to 4 meters. Yeah, so that's the first step. Then we look at the second one. Okay, now I look at the second one, the incident wave height. So how is the incident wave height? So that's what we need to find out. At the node, the water level range equals HI minus HR. What is that? That's a water level range. That's at a node. So at the node, we have this one. So that's over here. So we have HI minus H1. And at the antinode, do we have that? At the antinode, so we will have this range will be HI plus HR. Okay, so that's two relationship we are having. So for this one, we know first one is this. So from the chart, HI minus HR equals what? Roughly 1, right? From minus point, sorry, 0.1, yeah. From minus 0.6 to 0.4. So the range is 0.1, right? So that's 0.1. And then the water level range, so at the antinode, water level range, that's HI plus HR. So again, from the chart, we are able to see what's the range. This is a roughly 0.07, roughly 0.07, right? So I would say that is a more like 0.14 meter. Then by solving these two equations, that's just a simultaneous equation with two unknowns. So we will be able to, yeah. So we will have HI equals to 0.12 meter, and we will have HR will be 0.02 meters. So K will be equals to, sorry, not K, we use a C. So CR will be equal to HR over HI, which is this is what we have. For this one is 0.17. So we only have 17% of the wave has been reflected. Then we will get that partially reflected wave format. So using that, easily for you to calculate the reflection coefficient. So any questions? So yeah, if no more question, we will stop here today. And for the today and the yesterday, we covered or we reviewed the fundamentals about the waves, from the linear wave theory to the natural wave, and some basic or fundamental analysis techniques from the different distribution for the short term and also extreme and also long-term analysis. And also here, we also talked about the wave transformation. So in tomorrow, we will see the application of what we learned here, how we applied that to the beach, the sedimentation modeling. So we are going to use either Python or MATLAB, because here we couldn't install MATLAB. So, and also my laptop, I cannot reach the network license. So I will show you the Python, the code over here. But you feel free, like whatever you want to use. Yeah. Okay, thank you, and see you tomorrow.